In this module, we are going to learn competitive firm under uncertainty. Traditionally, under perfect competition, the prices are given to the firm which have to respond by producing the profit maximizing quantity. No lag is assumed to take place between the decision to produce and placing on the market of the output. Hence, the price that prevailed when the decision to produce was taken was also the price that prevailed when the product was marketed. There was no reason why the two prices should be different. The price is a definite given amount. Secondly, the firm had no difficulty in producing the unique profit maximizing quantity at the given price. This is because there was a given relationship between the inputs and outputs, which allowed the firm to produce a definite quantity. However, production is a process that takes time and is therefore not instantaneous. There is a possibility that the price that may have prevailed at the time when the production process was started would be different from the price that would prevail when the production process was completed and the output placed on the market. The price that would prevail when the product was placed on the market would be affected by the state of nature, which is beyond the control of the firm and is not known to the firm at the time when the firm started to produce. There could be alternative states of nature, the firm would know none of which in advance, but which could be assumed to occur with certain known probabilities. The firm would have to base its production decisions on a probability distribution of possible prices. This is a case of a firm being subjected to price risk. Production too is affected by the states of nature, which again are not known in advance. Hence, the level of output is not determined by the inputs, but is stochastic in nature depending again on states of nature which are not known in advance. In agriculture, for instance, there is the impact of weather and diseases which depend upon the states of nature and are not known in advance. Here again, the firm has to take into account the stochastic nature of production in its production decisions. This is a case of a firm being subjected to technological risk. A firm can be subjected to either to price risk or technological risk or both price as well as technological risk. The decision that it takes under these alternative conditions would depend upon the attitude of the firm's owners towards risk. After studying this module, you shall be able to understand the need to comprehend the decision to produce by firms under uncertainty, comprehend the use of probability distribution while taking the decision under price risk, evaluate utility maximization outcome under price uncertainty, identify the impact of element of uncertainty on the output produced, comprehend the application of Arrow-Pratt risk aversion function. We will commence this module with utility function. Assume a firm operating under perfect competition. It is assumed that the owner's utility function with respect to its profit is given by uy. In this utility function, y is the income of the owners given by y is equals to OC plus pi, where pi is firm's profit and is given by pi is equals to PQ minus CQ. Here P is the price, Q is the quantity produced and CQ is the total cost of production, which is a function of quantity. Here it is being assumed that the cost does not include the opportunity cost of inputs provided by the firm's promoters. This opportunity cost OC will be assumed to be constant. Under a long-term perfectly competitive equilibrium, profit is zero, but the owners get a return equal to their opportunity earning. In the long run, the opportunity earnings can be assumed to be return that could be best return that could be attained in an alternative use of equivalent risk. This opportunity cost is a part of total cost of production and can be assumed to be a part of the fixed cost in the short run. Hence, even though the economic profits are zero, there are positive earnings that the owners of the firm get. In the short run, however, the profit need not be zero and it is assumed that the owners are seeking a return over and above the opportunity earnings. The owner of the firm is assumed to have a utility function that is concave with respect to his income, so that the utility function is characterized by the assumptions u dash is greater than 0 and that u double dash is less than 0, where u dash is the marginal utility and u double dash indicates that marginal utility declines as income y increases. These two conditions together imply that marginal utility declines continuously but remains positive. It also implies that utility increase as income increases but at a declining rate. This is the utility function of a risk-averse economic agent. For a risk-neutral economic agent, the utility function would be linear with respect to y such that u dash is greater than 0 and u dash is equals to 0. In the absence of risk, maximization of utility would be the maximization of the firm's owner's income y, and the firm would then produce that level of output that maximize its profits as given by the traditional theory. Under conditions of risk, however, the objective would depend upon the firm's owner's attitude towards risk. Next, we will study the utility maximization output under price uncertainty. Consider the case where there is no risk, that is, there is only one state of nature and the price is known with certainty. The firm is assumed to maximize utility with respect to output. The first order conditions are u dash y dash is equals to 0, where y dash is the derivative of the owner's income with respect to output. This yields the derivative of the firm's owner's utility with respect to output. This first order condition could be expressed as u dash into OC plus PQ minus CQ into P minus C dash Q, which is equals to 0. The second order condition would be expressed as u double dash into OC plus PQ minus CQ into P minus C dash Q whole square minus u dash OC plus PQ minus CQ into C double dash Q. Since u dash is greater than 0 for all values of Q, first equation implies that for the first order condition to hold, P is equals to C dash Q, that is the output should be at the level at which marginal cost must equal price. Since P minus C dash Q is equals to 0 and u dash is greater than 0, the second order condition implies that C double dash Q is greater than 0, which is the same as saying that the marginal cost should be upward sloping at the level of output at which the marginal cost equals price. These are the traditional theory's equilibrium conditions. How are these conditions changed under conditions of risk, and what implications do they have for the equilibrium level of output? If there can be alternative states of nature that are not known to the producers ex ante, that is at the time when they decide to produce, then the price is not known with certainty. However, a probability of the various price levels dictated by the alternative states of nature are assumed to be known. Under these conditions, the owner's income will depend the state of nature, and since a probability distribution is assumed to over the various resulting price levels, the expected value of his income and hence utility can be calculated as EU bracket YN bracket close, where YN is the income under the nth state of nature. It is given as YN is equals to PN into Q minus CQ plus OC. A simplifying assumption is that the opportunity return of OC is the same in the absence of risk and in situation of risk. Hence, the expected value of utility will be EU YN is equals to EU PNQ minus CQ plus OC. Under these conditions, the equilibrium condition will be altered to be expressed as EU dash OC plus PNQ minus CQ into PN minus C dash Q is equals to 0. EU double dash OC plus PNQ minus CQ into PN minus C dash Q का whole square minus U dash OC plus PNQ minus CQ into C double dash Q, or capital D is equals to EU double dash YN into PN minus C dash Q whole square minus U dash YN into C double dash Q is less than 0, where last two are the first and the second order conditions respectively. Assuming C double dash Q is greater than or equals to 0, the last equation will always be a negative value. While under conditions of certainty in which the price is anticipated with perfect certainty, a firm will choose a definite level of output at which the marginal cost equals the perfectly anticipated price. It will not be the case where the state of nature and hence the price is not known in advance. Since the decision to produce is made ex ante, that is before the state of nature is known, it is unlikely that the income and hence the utility will be maximized ex post when the state of nature and hence the price is revealed. That is, the maximization of income and utility is unlikely at Pn is equals to C dash Q, that is at Q bracket Pn bracket close, unless the state of nature has been correctly anticipated. Hence, the firm will not produce a level of output corresponding to any one of the price associated with their respective state of nature. Let us assume that the price P has the density function Fp. The expected value of price P random variable is given as Ep is equals to mu. As a result, the value of mu is non-negative. The first order condition can be written as E u dash into OC plus PNQ minus CQ into PN is equals to E u dash into OC plus PNQ minus CQ into C dash Q, or in terms of Yn it can be written as E u dash Yn into Pn is equals to E u dash Yn into C dash Q. Subtracting E u dash Yn mu on each side of the above equation, we get E u dash Yn into Pn minus mu is equals to E u dash Yn into C dash Q minus mu. Yn is equals to PNQ minus CQ plus OC. Yn is equals to E Pn into Q minus CQ plus OC. Yn is equals to mu Q minus CQ plus OC. From last two equations we conclude Yn is equals to Yn plus P minus mu into Q. Therefore, it is clearly evident that u dash Yn is less than equals to u dash Yn if P is greater than equals to mu. It follows that u dash Yn into Pn minus mu is less than equals to u dash Yn into Pn minus mu. The above inequality will hold for all Pn greater than equals to mu, but for Pn less than equals to mu will reverse inequality in third last equation, but while multiplying by Pn minus mu will hold second last equation still the same. Taking expectations both sides, we get E u dash Yn into Pn minus mu is less than equals to u dash into Yn into E Pn minus mu. This would imply the right hand side of the above equation is 0 since Ep is equals to mu. As a result, the left hand side becomes negative. This further implies right hand side of the last equation is also negative, and it can be written as E u dash Yn into C dash Q minus mu is equals to E u dash Yn into C dash Q minus mu, which is less than equals to 0. Since marginal utility is always positive, this would mean C dash Q is less than equals to mu. This further reveals that the optimal output is characterized by marginal cost less than the expected price. From the last equation, it can be deducted that under the situation of certainty, the cost curve associated with competitive assumptions are the ones which have marginal cost either increasing everywhere or U-shaped. Consider an increase in risk leading to expanding of probability distribution around a constant mean. Assume there exist both a multiplicative and one additive shift parameters, due to which price can be written as Yp plus theta, where y is the multiplicative shift parameter and theta is additive. It also implies that d e yp plus theta is equals to 0, e p into dy plus d theta is equals to 0, mu dy plus d theta is equals to 0, and d theta by dy is equals to minus mu. Substituting new price incorporating increase in risk, yn in yn is equals to pnq minus cq plus oc, we obtain yn is equals to yp plus theta into q minus cq plus oc. Differentiating above with respect to y, taking into account d theta by dy is equals to minus mu, we get delta q by delta y is equals to minus q into 1 by capital D into e u double dash yn into pn minus q into pn minus c dash q minus 1 by capital D into e u dash yn into pn minus mu, where D is equals to e u double dash yn pn minus c dash q whole square minus u dash yn c double dash q. The left hand side delta q by delta y represents impact of uncertainty captured by y on quantity produced. Since D term as from fourth second order condition is a negative value, the second term becomes negative. However, the first term is indeterminate, therefore the marginal impact of uncertainty cannot be established. Suppose we start from the situation of certainty, which implies P is equals to mu, further replace the certain price of probability distribution. When price is known to be equal to mu, then C dash q is equals to mu, and the first term of last equation becomes q into 1 by capital D into e u double dash q p minus mu whole square. The above term is completely negative. As a result, both the terms in last equations are negative. This establishes the overall impact of uncertainty on firm's output, which is negative. Now let us study another method for this. Suppose Q star is maximization outcome, that is unique solution of maximization problem. In order to investigate sign of delta Q star by delta y, we consider the last equation. Delta Q star by delta y is equals to minus Q star into 1 by capital D into e u double dash yn star into pn minus mu into pn minus c dash q star minus 1 by capital D into e u dash yn star into pn minus mu, where capital D is less than 0. Modifying e u dash yn star into pn minus mu equals to e u dash yn star minus e u dash yn star into p minus mu is equals to covariance of p and u dash yn star, where covariance of p and u dash yn star is the covariance between p and u dash yn star. Differentiating u dash yn with respect to p at q is equals to q star, we obtain delta u dash yn by delta p is equals to q star into u double dash yn star, which is less than 0, which means covariance of p u dash yn star is less than 0. In such case, the competitive firm faces price uncertainty. Using last two equations, we get e u dash yn star into pn minus mu is less than 0. Considering the first term of the last equation, e u double dash yn star into pn minus mu into pn minus c dash q star, modifying the above, e into p minus c dash q star into u double dash yn star into p minus mu, which is equals to e p minus c dash q star into p minus c dash q star plus c dash q star minus mu into u double dash yn star equals to e p minus c dash q star whole square into u double dash yn star minus mu minus c dash q star into e p minus c dash q star into u double dash yn star. In last equation on right hand side, first term is negative and second term is non-positive. Therefore, q star into e p minus c dash q star into u double dash yn star into p minus mu is less than 0. Using the previous equations, delta q star by delta y as negative, considering capital D less than 0, this establishes the fact that with introduction of element of uncertainty, the equilibrium level of output produced by the firm gets reduced. Moving on to Arrow-Pratt risk aversion function. It is possible to have a quantitative measure of how averse to risk a person is. The most commonly used measure of risk aversion was initially developed by J. W. Pratt in 1960s. This risk measure is denoted by R capital W. R capital W is equals to U double dash capital W divided by U dash capital W. Since the distinguishing characteristic of risk-averse individuals is their diminishing marginal utility of wealth, this implies that the Pratt's measure is positive. This measure is invariant with respect to linear transformations of utility functions. In such case, Von Neumann Morgenstern ordering is used. In the given case of competitive firm under uncertainty, restrictions on utility function may be introduced by the means of the Arrow-Pratt risk aversion functions. Absolute risk aversion. Capital R A Y N is equals to minus U double dash Y N by U dash Y N. Relative risk aversion. Capital R R Y N is equals to minus U double dash Y N into Y N by U dash Yn. Capital R A Y N is the decreasing function of Yn, indicating the fact that as the decision maker becomes wealthier in terms of income or profits, his risk premium for any project or investment defined as difference between the mathematical expectation of return from the investment and its certainty equivalent should decrease or at least not increase. Let us now summarize what we have learnt in this module. Under perfect competition, the price is given to the firm which has to respond by producing the profit maximizing quantity. No lag is assumed to take place between the decision to produce and the placing on the market of the output. The production is a process that takes time and is therefore not instantaneous. There is a possibility that the price that may have prevailed at the time when the production process was started would be different from the price that would prevail when the production process was completed and the output placed on the market. The marginal utility and the second derivative of the marginal utility declines as income Y increases. These two conditions together imply that the marginal utility declines continuously but remains positive. Introducing uncertainty in prices leads to calculation of expectations and finally establishes that overall impact of uncertainty on firm's output is negative. It is possible to have a quantitative measure of how averse to risk a person is. The most commonly used measure of risk aversion was initially developed by J. W. Pratt in 1960s.